Okay, well, good morning, everybody. I got 10:30 on my watch up here, so I'm going to go ahead and get started. I got a lot of slides to go through. Thank you for coming. I'm glad to see this many people here interested in what I'm going to be talking about. If you haven't figured it out yet, this is Forensics with Linux 101, or as I prefer to call it, How to Do Forensics for Free. Because any of you who've done computer forensics using commercial packages knows that it's a very expensive proposition to buy those packages, and I'm going to show you how you can do a lot of the stuff that you need to do without costing you anything. And as on the slide, my name's Chuck Willis, and I'll be talking to you for the next hour and a half. I guess we have until 12 o'clock. I know everyone's excited to go to lunch, so I'll try to move through it quickly on the parts that need to go through quickly. This is the agenda of what I'm going to be covering. You can see, if you're flipping through the book or looking at the CD, there's a lot of slides. I've got about 88 slides that I'm going to be going through, which I did as a conscious decision that I wanted to put more information in as opposed to less, but it does mean that I'll be moving through some of the material pretty quickly. If you have questions, feel free to ask, or if you have more in-depth questions, I'll be happy to answer after the presentation or any other time. But we're going to start off with a little introduction, and talk a little bit about why you would want to use Linux for forensics, then kind of talk about what you do before you make your forensic image. For those of you who aren't familiar with computer forensics, the gist of the process is you want to take your original evidence, you make an exact copy, and then you do all your analysis on the copy. So we'll be talking about what to do before you make that image, how to actually make the image, how to go through preparing your analysis system, how to do the analysis, and then we'll wrap it all up. It's a lot of stuff to talk about. Most of the presentation is basically lecture that I'll be showing slides and talking about because I didn't want to demonstrate a lot of fairly mundane things. I will be doing some demonstrations at the end when I talk about conducting the analysis. So that's why I'm going to move through a lot of the beginning stuff quickly, because a lot of the really interesting stuff is at the end. For those of you following along on the CD, here's kind of a little table of contents of what's on there. This presentation is on there, a slightly dated version. There's also seems to be someone else's presentation in my directory for some reason. There's a README file that somehow ended up in Unix format. So if you try to look at it on Windows, it's going to show up without any line breaks. If you look at it on Linux, it looks fine. That kind of tells you what else is on there. There's an HTML file which has basically hyperlinks you can follow to all the stuff I talk about here if you want to get on the web. There's a binary distribution of some kernel, basically a modified kernel that was made by NASA that I'll talk about later. Source code to the rest of the tools that I talk about. There is one file system image there. It's an ext3 file system that contains some graphic images that you can use for both looking at them with Autopsy and SleuthKit, and also Foremost, which I'll talk about later. And there's also some text files with a lot of various details that you may or may not be interested. What was supposed to be on the CD that didn't make it was the actual image of about a 350 megabyte hard drive that I'm going to be using for analysis later. So unfortunately that didn't make it. There were some problems with burning the CDs. But if anybody has a website that they want to put actually it's about 85 megabytes compressed, please give me an email or something. I'd like to put that out where people can get to it. And if you want to find it later, give me an email. My email address is on the presentation. Okay, so a little bit about me. I've done a lot of computer forensics, primarily using commercial tools. Ncase, if any of you've heard of it, it's about a $2,000 or $3,000 software package that is actually very good for doing forensics, but it's also very expensive. I've not written any computer forensics tools, and I say that for two reasons. One being that I don't want to be seen as trying to take credit for things that other people have written. All the tools I'm talking about today were written by other people significantly smarter than myself. And I don't want to be seen as trying to take credit for what they've done, and I've cited them in the presentation. But also I feel myself that I am a unbiased observer in this whole issue, basically, and I talk about the tools that I think are good and don't talk about the tools that I think are bad. So I like to think of myself as independent in that way, and I'll leave that to your own judgment to decide if that's true or not. I don't work for any company that sells computer forensics tools, so I have no interest in that sense either. I'm here only representing myself. I'm actually just in the process of separating from the Army, but they did want me to say that I don't represent the Army anymore, or never did actually. And I'd also like to yeah. I'd also like to say that I'm not a Linux zealot. I'm running PowerPoint on this laptop here because I think it displays better. I use the right tool for the right job. And so I'm not saying that you should use Linux for forensics just because I want people to use Linux for everything. I think it's actually a good tool to do the job. Okay, a little bit about this presentation. As I mentioned, ask questions at any time. I have not done any exhaustive testing on these tools. They may destroy your evidence, they may kill your dog, they may blow up, I have no idea. But it's basically it's your own risk. So if you want to follow my advice, go ahead, but it's just advice. I'm not preaching the gospel or anything. And I'm going to give the limitations and the benefits of the tools as I understand them, but again, I didn't write the tools. There may be features that I don't understand and all that. So I'm doing my best. And one of the things I'm going to say straight up front is that doing forensics with Linux is not right for everybody. And there's a few reasons for that. One of them is that the tools are not as easy to use and they're not as full-featured as the commercial packages that are out there. So if your full-time job is to do computer forensics, then you probably need to buy tools that do that. However, it's always good to have multiple tools in your bag, and you never know when the $3,000 forensics suite that you bought is going to crash on the hard drive you want to examine, and you need to go to a backup plan. So, but it's not, I would not recommend it as a primary means of doing forensics if that's your job. But there's a lot of people who are normal security professionals that mainly do IDS work and firewalls and all that other stuff, and occasionally have to do forensics on a system that's been intruded upon. Then Linux may be the right solution for you because the price is certainly right. I'm assuming everyone here has heard of Linux and knows about the command line and how to type things and that sort of thing, so I'm not going to talk about that or explain any of that. I'm also going to primarily be talking about analyzing an IDE hard drive, but a lot of the techniques will work basically the same way for CD-ROMs, floppy disks, SCSI drives, all that kind of thing. Some of the techniques I'm going to talk about are really geared towards basically Linux or Windows systems that have a standard DOS-type partition table. So a lot of the tools can be used on other systems, but it needs to have a little bit different flavor to be able to read things like BSD disk labels and that sort of thing. And I'm only going to be talking about dead disk forensics. So I'm assuming that the system you want to analyze has already been turned off, you've taken the hard drive out. I'm not going to be talking about doing live analysis or incident response or remote data acquisition or any of that kind of stuff. It's dead disk forensics because I only have so much time to cover this. So that's the introduction. Now a little bit about why you'd want to use Linux for forensics. And I don't want to dwell on this, but I do want to mention it because I feel I probably should if any of you are on the fence about whether you want to use Linux to do forensics or not. The biggest advantage, as in the subtitle of my presentation, is the tools are free. Both free as in you don't have to pay anything, and free as in open source. So if you are not going to use them very often, then it's a good system to use as far as you don't have to pay the money up front. The fact that they're open source is also good for a variety of reasons, and a lot more of it is detailed in that paper there by Brian Carrier. But it allows you to know exactly what the tool is doing if you want to read through all the source code. It allows you to make modifications to the tools if you need to. There's a lot, all the normal advantages for open source software. The environment is also very flexible. There's a lot of things you can do just with the standard tools that are built into the Linux operating system to manipulate data files and be able to read data off and that sort of thing. So there's a lot of flexibility. A lot of that comes from the whole Unix philosophy that everything is a file. So you can do a lot of the manipulations on things that you wouldn't normally think you could. It's certainly a lot more flexible than something like a Windows or a DOS environment. And when the tools are used properly, the evidence should stand up in court. I'm not a lawyer. I don't know of any specific court case that has gone with Linux forensics tools being used, but I would be surprised if there wasn't one. But consult your lawyer if you're going to rely on that advice. The first three limitations of using Linux are actually pretty much the same as the advantages. First being that you don't get, because the tools are free of charge, you don't get tech support. You don't have someone you can call in the middle of the night and say, that your tool isn't working, I need it fixed by tomorrow. You don't have someone that you can say, I'm going to court, I need you to come and say that your tool is appropriately analyzing the evidence and that sort of thing. So you kind of get what you pay for in that respect. The tools are open source, which can lead you to problems if you do go to court because you've got to consider that the defense may stand up someone and say, well, you use this forensics tool that's open source, and we had an expert look at that forensics tool and found 50,000 bugs in it. Were you aware of those bugs? Did you look through the source code? For the most part, I consider that more FUD than anything else, but it is something to be aware of that may be a problem. Getting my picture taken as well. I was trying to look away from him, but he caught me. The environment is also very flexible, which kind of leads to the problem that there's a lot of different ways to do the same thing, which is very true of most Linux type things you want to do, which causes problems in that there's no universally accepted standard operating procedures that everyone knows, well, if you're going to do this, this is what you should do. It's kind of, there's lots of different ways to get to the same place, which could also cause you a problem if you go to court, because they could get 10 defense experts that say that what you did was not what they would recommend. So just something to be aware of. As I mentioned earlier, the free tools that I'm going to talk about are not as full-featured as commercial packages, or some of you may have heard of a tool called iLook, which is basically a free computer forensics package, runs on Windows, but it's only available to law enforcement and government personnel. So if you can get a copy of iLook, definitely get it and take a look at it. But I assume a lot of you don't have access to that. So it's kind of, you're either going to have to spend money or you're going to have to use what I'm going to talk about. The tools are also significantly more complicated. A lot of them involve command line. A lot of them really follow the Unix philosophy of lots of little tools that you can kind of all put together to get what you need. So a lot of times you're going to have to kind of break the problem apart into smaller pieces and go through it. A lot of that has been fixed with the autopsy browser that Brian Carrier has written, but there are still other things you want to do that are not included in that. And also in many of your operations that you want to do, because you're on the command line, a little typo can destroy things, especially when you're doing your imaging. You mix up the input file and the output file, you can have yourself a lot of problems. So you just need to be aware of that, and it just kind of comes with the territory, unfortunately. One final limitation I'm going to talk about only very briefly is that Linux has a problem that if you have a hard drive with an odd number of sectors, that it cannot see that last sector. It's something to do with the kernel buffering, that it actually reads data in 1K chunks or something. I'm not really sure exactly why that is. You will probably never ever see a drive with an odd number of sectors. The only ones I've ever heard about are very old SCSI drives. But just be aware it's a limitation. If you do come across one, then you need, if you want to actually continue along the path I'm showing you, you can use a BSD variant to do your imaging. I'm not sure if the analysis is going to be affected by that or not. It's kind of, you're on your own, but I don't think you're going to come across that, so I wouldn't worry about it. Okay, now we're moving on to preparations. Now, by preparations, I'm kind of talking about now, this is kind of setting up what we're going to be doing later and preparing to connect our evidence to make an image. So, just kind of an overall of what I'm going to talk about. Well, I've got a variety of things that I kind of want to lay out. I'm assuming you've got a forensic analysis system that's running Linux, and that's my laptop over here. That basically it's basically a standard Linux install. You've installed some additional tools to do forensics and that kind of thing. Now your imaging, when you do forensic imaging, you don't want to do it on that system. The reason being that you're going to be constantly adding new tools and that kind of thing to your analysis system, and you don't want to be worried every time you add a new tool or compile something that, well, did that RPM I installed make changes to the file system table as far as the auto mounting and that sort of thing. So when you do your imaging, you're going to be booting off of a boot CD. That will be a controlled Linux environment that you can do your forensic imaging on. Now it could be the same computer system, but you wouldn't boot off that hard drive that you've got all your tools on. You would boot off the CD. And then I'm assuming you have an evidence hard drive that has whatever on it, basically any operating system. And you've also got what I call an image hard drive, which is where you're going to write all your data files to for this analysis, so that you can use your same forensic system for 20 cases without having to worry about cross-contamination between the different cases. So you write all the data, you write your image onto the image hard drive, and then all the analysis that you do when it's pulling files off the image, you put it on that CD, that hard drive as well. So that's kind of the setup now. The boot CD we're going to be talking about is the Fire Boot CD by William Saluski. It's actually a very nice little environment. There's the website. You can download it and burn it. It's very similar to Knoppix and other tools like that, but it's designed for forensic and incident response, which is the good thing about it. So it's really, all the tools that he adds and all the things that he does to it is designed to preserve the evidentiary integrity of your original when you boot off the CD. So it doesn't mount any of the partitions. It doesn't use any of the existing data structures on the disk. So that's what's good about it. And one of the bad things about it, as I mentioned here, is that by default, the shells that it opens come up with VI style editing, where you've got to use like the X and the I and the capital A and all that kind of stuff. But if you write this little set-o Emacs in each shell you open, it will actually change it so you can do more normal editing. By editing, I'm talking about like if you type a command and you need to go back and type it again or fix a typo or whatnot. Okay. There are several alternatives to Fire out there. I mentioned Knoppix. Knoppix, the older versions had some evidence contamination issues, whereas if you booted a Knoppix CD on a Linux system, it would use the swap partition on your hard drive, on the evidence hard drive. which obviously is a bad thing. It contaminated your evidence. I think the newer versions have fixed it, but I'm not sure. A couple people have created modified versions of Knoppix for forensics. I haven't used them, but there's a couple of them right there. My real philosophy on it is that if you take something like Knoppix that is not designed for forensics and try to make it into something for forensics, it's just necessarily more complicated than it needs to be. That's why Fire is good. It's designed from the ground up for that. Yes? Yeah. Oh, he just mentioned that if you've got Knoppix, you can boot with the no swap option when you boot the kernel, and that will keep it from using the swap partition. And there's other stuff out there, Tom's Root Boot, there's other Plaque, I think there's some other ones out there. But again, they're not designed for forensics, they're designed for other stuff, and that's why I like Fire. I would like Fire even better if it was only designed for forensics, because even all the incident response stuff that it includes is just a bunch of tools that you really don't need. All we're concerned about is the forensic stuff on it. Okay, now we're going to get ready to image. So we've identified the hard drive that we want to image. We're going to look at it and say, okay, what model hard drive is it? How big is it? And particularly we want to note the total number of sectors that are on the drive, because that's what we want to use later to verify we're actually seeing the entire drive and are making a proper image. Then we're going to want to find an image drive to write our image onto. I say about 3 times the size of your evidence is a good rule of thumb, because there's overhead for the file system. We've also got a lot of data extraction and stuff like that that's going to happen later. It's better to be too big than too little. However, if you've got an evidence drive that's 200 gigabytes, then you may have to make some adjustments. May have to make a RAID or something to write your image onto. I don't know. We're going to want to wipe our image here. That's this command here, dcfldd, and I'm going to talk more about that later. And actually, that command has changed a little bit from probably the slide you have in front of you if you're following. The no error sync is not really necessary when you're wiping, because it only deals with read errors. But I'm going to talk more about that later, but I just wanted to say if you want to wipe your drive, which is recommended if you're going into court later, it's good to say, well, the drive I wrote my image onto, it was completely wiped. I know there was nothing on it before I started. So you wipe it, you create a partition, reboot it, you make a file system. I prefer to do that on the Fire boot CD, especially because if you're wiping a drive, you want to make very sure you're wiping the right drive. So I like to boot off the Fire boot CD, and that's the only drive that's on there is the image drive, so you make sure you're wiping the right one. And if the dev HDA is if it's the primary master, obviously you would make corrections if it's different. So then you want to go ahead and mount your image drive. You're going to create a couple directories. This is more bookkeeping stuff that I'm going to rush through. But you want to create a separate case number directory on this drive, so you've got kind of a hierarchy of where the stuff came from. You've got the case number, and then you also have the evidence number. So if you've got one incident where 3 systems were broken into, that may all be part of one case, but it's 3 separate pieces of evidence. So it's more just to keep stuff straight. You're also going to want to create what's called an evidence locker, which is a directory that Autopsy will use later in the root of that drive as well. And then you just want to create a little text file about the case, just your name and some other information, along with a text file about this piece of evidence. The reason you're doing that is because if you've ever worked in a computer forensics lab, you'll know that occasionally you'll come across a hard drive that no one has any idea where it came from. And you're like, well, this is a forensic image, but I don't know whose image it is. I don't know when it was made. I don't know why we were looking at this system. Or you may yourself make the image and then go on vacation or get busy with other stuff, and you come back to do the analysis 2 or 3 months later, and you can't remember well exactly which image was which IP address and which host and all that kind of stuff. So it's just good bookkeeping information to have. So that's what I recommend. Well, now we're to the point where we've done all the kind of administrative stuff on the front end. We're ready to connect our evidence. So go ahead and connect your evidence drive and your image drive onto the system. Make sure you check the old master-slave cable select jumpers. There's various debate on what's the most high-performance way to do it. Do you put both the hard drives on the same chain as the master and slave? Do you put them as separate as both master? I think it really depends, because I've heard people that really advocate both ways. But in general, all the stuff I'm talking about here, I'm more concerned about getting a correct image than a fast image. So I kind of say, well, don't worry about it. But if you're, again, imaging a 200 gigabyte drive, then performance is probably going to be a significant concern of yours, unless you want to spend a couple weeks making your image. And you obviously want to make sure your BIOS is set to boot only from the CD, because you don't want to accidentally boot your evidence and cause yourself trouble there. So you boot from your Fire boot CD. It comes up and gives you an option very much like any of those other Linux things that you can boot into X Windows or console mode. I prefer to go to console because there's really no reason for X Windows, so just keep it simple. It's really less is more kind of thing when it comes to forensics. You want to have less processes running, less things that might be accessing the disks, all that kind of stuff. So boot option 1, when you boot into console mode, it displays a nice little menu, which unfortunately I can't figure out how to exit out of. There probably is a way. But you can always just change to another virtual terminal. Just do the old Control-Alt-F2, switch, then you just have to log in. The root password is fire, and it doesn't tell you that, so you have to kind of dig that out. So that's a good thing to remember, fire. One of the things you don't want to do is mount your evidence partitions, because now this is assuming you've already decided, yes, I know I want to image the system. If you're in a situation where you're like, well, I want to preview it and kind of see if I need to image it or not, then that's a whole other thing. But you really need to be careful with mounting your file system. Even if you mount the file system read-only, there are issues in journaling file systems where it actually makes changes to the journal. It prevents you from making changes to the files, but it will make changes to the journal when you mount them. That's basically ext3 file system or RiserFS. So, but at this point, like I said, I'm assuming you already know you want to image the drive, so there's no need to mount them at this point. You might as well just go ahead and make your image. Okay, but one of the things you do want to make sure you can figure out is which hard drive is which. You've got your image hard drive and your evidence hard drive. And the way you do that is with the dmessage command, which gives you all your boot message, basically all the boot information that the Linux kernel gives you. Dmessage, and you just pipe it to grep HD, which will give you information about the hard drives. And you can see here that you've got HDA is this Western Digital 30 gigabyte drive. The capacity is actually down there. And HDC is this IBM drive. So you now know HDA is the Western Digital, HDC is the IBM. And in this instance, HDA is actually the evidence hard drive that we want to look at. That's the primary master. So we're going to be writing it onto HDC, which if you're wondering why we're going to write a 30 gigabyte hard drive onto a 14 gigabyte hard drive, it's because I only created like 3 100 megabyte partitions on this drive, and we're only going to image about the first 350 megabytes of it. So there's plenty of room. Yes? Yes. Well, right. Well, the absolute minimum is you probably need, I would say, about 5% more than the evidence drive. And what you could do is you could have 2 separate drives where you may want to image from the evidence onto an image drive, and then later when you want to do more analysis and extract stuff and all that kind of stuff, write that onto a whole separate drive. But you are going to need about, I would say, about 5% overhead, because you're going to have, because you're not copying directly from one drive to another, you're copying from one drive to a file on the other drive. So there's file system overhead and that sort of thing. So I would say about 5%, but then you're going to have to write all your data later to other things. Any other questions at this point? Okay, we figured out which hard drive is which, as I mentioned here, and it's very, very, very important to keep these straight, because now you're going to turn around and mount the image drive read-write, which is obviously going to cause huge problems if you mount your evidence read-write, and you're going to actually image the drive onto that one. So now that we know that HDC is our image drive, we mount the partition. You may have to create this directory. I don't remember if Fire creates that for you or not, the mount HDC1. Then we go ahead and change to the directory for this piece of evidence. And now we're going to just kind of do a couple bookkeeping things to extract a whole bunch of information that may or may not be useful later. We're going to do the dmessage, which is all the boot information, and dump that to a text file. For those of you who aren't familiar with the T command, it basically displays stuff on the screen at the same time it's writing it to a file. So it allows you to see what it's doing along with writing it to a file. Well, then we're going to use HDParm, which some of you may have heard of for doing performance tuning, but we're going to use it actually to just get the information off the drive. And the options we want to use are dash lowercase g, lowercase I, uppercase I. The order isn't really important, but the gist of what that's going to do is going to give you the geometry of the drive, and it's also going to give you information about the drive. I forget which is which, but one of the I's does the information from kernel, so it's kind of what the kernel thinks the drive is. The other actually reads directly off the hardware. In theory, those should match, but they may not, so it's good to get both. I've seen instances where the serial numbers on different parts of the thing don't match, and I haven't been able to reproduce it, and maybe I was just crazy that day, I don't know, but it seemed like it was having endian problems where it was actually reversing bits of the serial number, so just be aware of that. One of the things that people are concerned about, depending on how paranoid you are and what exactly the circumstances of the case are, is what's called a host protected area, which is basically a way that you can have an IDE hard disk that has kind of a little area of it that, or a big area potentially as well, that is kind of cordoned off and not seen by the operating system. And that's a good place to hide data if you want to do it. A lot of the manufacturers like Gateway and Dell and stuff may use HPAs as a way to store system restore information for people that are too lazy to put a system restore CD in their computer. So, wow, is that me or is that somebody else? That's not this one. Well, anyway, I'll just go on. Where is that coming from? Is that like a fire alarm or something? It's rather ear-shattering. There we go. Anyway, HDPARM. Oh yeah, there we go. Thanks for fixing that for me, by the way. HDPARM can also be used to adjust your hard drive settings for performance reasons. Like I said, if you're looking at a 200 gigabyte hard drive, you may want to mess around with these. I prefer not to because I'm more concerned about getting a correct image than a fast image. But it really kind of depends on your own preferences there. This is kind of the output, what it's going to look like. And I've circled a couple of things that are important. The top is the geometry. It tells you the number of sectors that's circled. It also tells you the model number, the serial number. Number of sectors, again, on the next page it shows you more serial numbers and number of sectors. Basically, you just want to make sure all those number of sectors matches up with what the hard drive is supposed to have, either from its label or if you're paranoid from the website based on the model number. Because that's going to tell you, one, that you've actually got the appropriate, your Linux is actually seeing the entire drive, and it probably means that you don't have an HPA, although I haven't really tested that. The other reason that I talk about HPAs is because people see this little blurb here that says host protected area feature set enabled, and they think that means that it has an HPA on the drive. All that means is that the drive supports HPAs, but it doesn't necessarily mean it has one. So anyway, that's what you do with that. The other thing you want to do is list the partitions that are there, and I use sfdisk for that. The options that you use are the dash lowercase l, lowercase u, uppercase s. And the reason for that is the uppercase S is pretty important because it lists a number of sectors, because that makes it easy to extract the partitions later if you need to. You can see this drive we're looking at here has 3 hard drive partitions, and it lists HDA4 even though there actually isn't another partition. So it's one of those things that you see them all, but you see you've got a Linux partition, an HPFS, NTFS partition, and a FAT32 partition. So. And again, that's going to be teed out to a file so that you've got a record of the hard drive partitions, especially if you're going to want to later go in and extract stuff off of those partitions, extract those partitions out of the entire disk image that you're creating. We're also going to want to hash, and this is one of those things that you can decide whether you really want to do it or not, but a lot of people like to create lots of file hashes when they do stuff like this, and you may want to hash all your text files that you've created about with the information about the sfdisk output and the HDPARM and the dmessage output. MD5 sum will do all that. But the one thing you are going to want to do is you're going to want to hash the entire drive. And that's just so you know, this is the kind of the baseline, this is what we want to have, and you're hoping that when you image the drive, it's going to come up with the same hash. That's the ideal situation. It doesn't always happen. But MD5 sum will do that. For those of you who aren't familiar with it, it basically just creates an MD5 hash of the original drive. And you just give it the raw device name of the evidence drive, so dev HDA. Pipe it out to T. This is going to take quite some time. I haven't done any real performance metrics to know. It's probably going to depend a lot on the performance of the hard drive and the performance of the system and all that kind of stuff. But I would say, for an average, 20, 30 gig drive, you're probably looking at an hour or two at least. So just be aware that that's going to take a while, but it's a necessary evil when it comes to doing computer forensics. And that's kind of sums up everything we should do before we image. And I break this into a separate section, the pre-imaging and the imaging, but be aware that there is not a real separation here as far as it's not like now that you've done your hash, you're going to shut down and start over. You keep the system running with the Fire boot CD. Now you're just moving in kind of the next step, which is the actual imaging process. Yes? No. It's not. All it's seeing is what basically the question, I'm sorry, I'm supposed to repeat the questions, was does it include spare sectors for drive remapping in the hard drive? And no, because all it's seeing is really what the BIOS is reporting back to the operating system. But basically the way that modern hard drives work is they will occasionally have bad sectors, and they will dynamically remap bad sectors onto other spare sectors that they have. But all of that is done at the firmware level on the drive controller itself. As far as anything outside the drive controller knows, it doesn't see those. Another question? Or are you going to? Mm-hmm. Yes. And to be honest, I've never heard of anyone actually doing that. If you want to do it, you're welcome. What it comes down to is then you're going to have to basically low-level access to the hard drive every time you want to access that data that you're hiding. Oh, the second part of it was basically if you wanted to hide data that way, then you could basically write data to some sectors, figure out what sectors they are, and somehow trick the firmware into saying that those sectors are bad. I'm not even sure if that's possible, to be honest, because it normally determines what are bad sectors itself by looking at it. There may be IDE functions or other low-level functions you could do to actually tell it that certain sectors are bad, but knock yourself out. Okay, imaging. A lot of people, when they hear about Linux for forensics, they hear about using DD for imaging. Well, it is the old standby, and it does work fairly well, but there are better options out there. One of them is RDA, which is also built into Fire, which basically takes DD and adds some remote data acquisition capabilities. We don't really need those functions, so I don't worry about it. What I do like, and it is built into Fire, which is one of the reasons I like Fire, is the DCFL DD, which is a tool that was written by Nicholas Harbour. He was then of the Defense Computer Forensics Lab. I'm not sure if he's still there or not. It's basically a modified version of DD and the biggest feature it adds is it shows progress while you're imaging. So you can know approximately how much you've imaged, how long it's going to take, that sort of thing. Because that's one of the very frustrating things. Imaging takes a tremendously long amount of time depending on how big the drive is and what your performance specs on your hardware are. So it's good to know that, yes, it's still working, it hasn't hung, and that sort of thing. It's got some online help, which is fairly unhelpful, but that's about all it comes with is the -- help option. But as I mentioned, it is included on the Fire boot CD. If you want it separately, you can actually go to the SourceForge page. The project name here, Beatrix, is actually a previous name for the Fire boot CD, I think, before he decided that was not a very politically correct name. So, but the source code is still available under that name. The options, and this again has changed a little bit from your slide. I added a couple things here. The main option you're going to give DCFL-DD is the input file and the output file, which is basically where you're going to read your data from and where you're going to write the output to. So the input is going to be the raw evidence device, so in this case dev HDA, and the output is going to be a file. So we're just writing it to another file. You actually could use DCFL-DD or DD or anything to actually make an exact copy of a drive to copy from one to the other, just specify another device name here. But again, that doesn't really help us all that much. We want to create a file because that's much easier to analyze. So you just create the output file. The two important things you want to specify are no error and sync. And what those do is normally DCFL, DD, or DD will just, if it comes across a read error reading the original drive, it just stops and gives up, gives you back a prompt, which is very annoying if you're 199 gigabytes through your 200 gigabyte drive. So you want to specify no error, which means basically if you come across a read error, keep plugging all the way to the end of the drive. But along with no error, you need to specify sync, because normally if it comes across a read error, if it comes across, so it reads 0, 1, 2, 3 on the original drive, it can't read number 4, then it just kind of skips over that and goes to 5, 6, 7, 8. So on your output, what used to be at 5 is now at 4. It's sector 4. So it basically shifts everything over. You end up with a smaller output file than your input file, and of course messes up all sorts of things like file allocation tables and partition tables and other stuff. So it's important that when you use no error, you need to use sync as well. Yes? If you have read errors on the drive, your MD5s probably aren't going to work out right. And it kind of depends on what kind of read error you have. And I haven't really done any testing on MD5 to know how it handles read errors, but I believe it basically is just going to either crap out completely or it'll just skip it over. But regardless, that probably isn't going to match up with what you get out of DCFL-DD. However, DCFL-DD has integrated hashing as well. And that's one of the other things we're going to use. It's better to have more hashes than not enough. So if it, for whatever reason they can't work, you can still use the hash that DCFLDD creates as kind of like the master hash that you want to be checking things against later. Okay, there's another option called BS, which is one that actually I don't use, but I wanted to mention it. It's basically, it means block size, not anything else. The default is 512 bytes, basically one sector, which is basically the smallest amount of data you can reliably, basically the smallest amount of data you can reasonably get off of a hard drive anyway. You can get better performance by increasing the block size. Basically, you can look at the HDPARM results and kind of see how many multi-sector reads it can do. 8K is a fairly decent amount. But the problem is if you have a read error, you lose the entire block. It basically will just zero out the entire block that you try to read. So one bad sector can end up costing you 8K of data that you've lost. So I usually just leave it at the default. Especially if you've got a large drive, you may want to just go ahead and use a larger block size like 8K, hope for no errors. If you do get an error, then you may want to go back and re-image using a smaller block size, or just leave it at the default. One more option for DCFLDD is the hash window option, or the hashing options. It's a bit strange. You have to specify hash window equals 0. The hash window option is really designed so you can have, like, if you wanted it to hash every 100 megabytes, you can specify hash window equals 100M. And it'll hash every 100 megabytes and produce a bunch of output. But all we want is one hash of the entire drive, because that's all we're really interested in. So, but you still have to specify a hash window and just put it equal to 0. And then you specify a log file, which is where you're going to write the hash output to, which is just a text file that gives you the output. It's also possible, this isn't integrated into DCFLDD, but through some other tricks, you can actually split while you're doing your imaging, either using a script or by piping it to split. I don't do that because later on, we're going to want to use the whole hard drive for analysis anyway. And that's why, by the way, we formatted our image drive ext3, because it supports very large files. Something like FAT32 can only support up to 2 gigabyte files. So if you want to image a drive larger than 2 gigabyte, you're going to have to split it. But again, I'm going to talk a little bit later about how you can split the image later for backup purposes. So here's the whole command that you want to use. Right here, you can read through all that. Basically what I talked about already. One of the things to be aware of, though, is do not confuse the input file and the output file, because then you're going to be writing what is basically an empty file onto your evidence. So not a good thing. So this is one of the instances where you really need to kind of sit on your hands before you hit the enter key and make sure that everything's correct. And again, you don't want to mess up the device names either, where you put in the wrong device name. You may have some problems as well. Okay. And when your imaging is done, like I said, DCFLDD will give you a nice progress indicator, which may move very slowly depending on what your parameters or your hardware are. Once it's done, you can just go ahead and do a shutdown -H now, shut down the system, disconnect your evidence, and put it in a safe somewhere because you don't need it anymore. And that's the good thing about the forensics process, is by creating a copy now, we can do all our analysis on the copy. So that's kind of finishes up the imaging. Is there any questions about that right now? Real quick? Okay, now we're going to move on to preparing our analysis system. And I'm going to move through this pretty quickly because it's basically just installing some programs, and I'll talk more about what the programs actually do later. But one thing to note is that you can prepare your analysis system before you do the imaging and before you even have evidence. But I put it here in the presentation because it seems to make the most logical sense. So you're starting your analysis system is, for the easiest way to do it is what I did, which is basically you have a Linux system, Red Hat. I use version 8. The reason being that there's some binary drivers you can download very easily without having to recompile your kernel and all that. Some of the packages are distributed as source. You may be able to find binaries out there, but it's easiest to compile from source. So you want to include everything, all the development packages on your analysis system and all that. Okay, the first tool I'm going to talk about is it's basically a modified kernel, but I refer to it as a driver. It's basically allows you to view an entire hard drive image as a loopback device. The Linux kernel includes a loopback device where you can basically mount a file as a file system. However, it will only look at one file system at a time, i.e. one partition at a time. By using these NASA drivers, you can actually basically use the integrated stuff in the Linux kernel to read the partition table, and will create multiple loop devices for you. It was written by these people. It's currently maintained by Jason Lutgens. and you can download it from here. It's included on your CDs. Unfortunately, some of the file names got kind of truncated on the Black Hat CDs. It's not all that big if you want to just go out and download them from that FTP site. One thing to note is that the binary distributions have different ones for different hardware architectures. And it's not really clear exactly what the different hardware architectures are and what hardware yours may have been installed on. So what you want to do is you want to look at your boot/kernel.h file to see what hardware basically configuration your Red Hat is using. Don't rely just, well, I know I have an Athlon, therefore I must have an Athlon kernel that I need to use, because you may cause yourself some trouble. There's some other files you need to download. Basically, there is I'll show them here. There's a create dev script, which basically kind of creates the loop devices, the modified loop devices. There's a loop utils RPM, which basically is the modified version of LO setup. You have to force that on because it's basically writing over existing files. There's the command line to do it there. The kernel, basically you just untar it into / and it puts itself in libmodules and boot and all that stuff where it needs to be. So it's fairly easy. The other thing you're going to have to do is you have to manually update your grub configuration or your Lilo configuration to add it. This is just kind of a quick gist of how to go about it. This is the before picture here. We got some other crap, and then Red Hat Linux here. Then you just want to add an additional one that's Red Hat Linux with NASA Loopback and put the new file names here. So it's not all that hard, runs pretty quickly. They also have source distributions as well if you really want to compile your own kernel with this stuff in it. One of the problems you're going to have is that that kernel that you're installing may not have support for things like your network device and all that. Like on my system here, my network card doesn't work if I boot to that kernel. But that's not a big deal really, because you really shouldn't be on a network while you're doing forensics anyway. You really should have an isolated system because you just want to kind of keep everything in one place. Another thing you might want to install, if you're going to install it, you should install it now, is the National Software Reference Library. It's basically a compilation of hash values from a whole bunch of programs. It's like 2 or 3 CDs worth, I think, at this point, compiled by the National Institutes of Standards and Technology. You can actually download an ISO from it. Normally you can't download an ISO, but I think they had some problems with one version, so they put it on their download site. You can download it from here. Newer versions, they're free to redistribute, but they don't want to pay for the bandwidth, I think, to do it. So if you want to get it, go get it now. The one thing to note about NSRL, and it's something that people sometimes don't understand, is that it does contain hacker tools as well. So it's not designed to be only known good operating system or application files. It's basically known files of any type, including bad tools. So don't assume that just because something's in the NSRL, well, I'm not interested in it. Especially if you've got like a network intrusion case, you may well be interested in some of the files that are on there that happen to be rootkits and exploits and stuff like that off the NSRL. But Autopsy asks for the location of NSRL, so if you're going to install it now before you install Autopsy. Sleuthkit and Autopsy, again, I'm going to talk more about these later, but it's written by Brian Carrier, who was originally at AtStake, which was why it was originally called the AtStake Sleuthkit or Task. It's based to a certain extent off of the Corners Toolkit, if you've heard of that, by Dan Farmer and that person that I can't pronounce their name very well, Venema. The Sleuthkit and Autopsy are kind of 2 separate tools that work together. The Sleuthkit is a collection of command line tools. Autopsy is a web server that you connect to with a web browser that allows basically a nice GUI interface to the Sleuthkit tools. And sleuthkit.org is the website. It's got the tools along with a lot of other great stuff on there. And it's pretty simple. I just put them in user local source, untar them, CD, make them, and it goes pretty quick. Autopsy is pretty much the same way. When you make it, it will ask for the location of the Sleuthkit and the NSRL if you have it. If you don't have NSRL, then you can just say don't worry about it. You also give it the default location for an evidence locker, which is where basically Autopsy is going to write all of its data files. You can put one in there, and you need to make sure that this is on a Unix file system that supports symlinks, as I found out when I was messing around with it. But, however, we created earlier a separate evidence locker for this case that's going to be on our image hard drive, and that's what you're going to want to specify when you run Autopsy anyway. So it doesn't really matter so much what you put there because you're going to use something different anyway. Foremost is another tool you're going to want to install. This is a disk carving tool by Chris Kendall and Jesse Kornblum, who's actually sitting right over there. A great little tool for basically doing what's called data carving, disk carving, or however you want to call it. It's basically, it looks at a raw data file, usually a forensic image, and will look for example, the JPEG header. And it knows, okay, I see a JPEG header. Now I'm going to keep looking until I see a JPEG footer, and then I'm going to take all that data in between, including the header and the footer, and write it out to a file because we think that's probably a JPEG. And then, so basically it's completely irrespective of the operating system that's running on that image was made of. So it will work on Windows, OS 10, CPM, I don't even know what the hell else you could do because it doesn't even care about the file system structures, it's just looking at raw data. And it's also very good for extracting deleted files because deleted files are still there. And depending on the operating system, it depends how much of the actual administrative data in the file system tables and stuff are deleted. But the data is usually still there. I don't know of any operating systems that by default overwrite the data, but some may for paranoid people. There's the website you can download it from, foremost, sourceforge.net. You just basically decompress it, go to the directory, make install, and it's done. So I'll talk more about using it later, but it's pretty easy. Okay, now we're to what's really exciting. We got 45 minutes left, so I'm doing okay here. Now we're going to talk about, we've got our system set up, we've got our image hard drive hooked up to our analysis system. Now we're ready to dig in and see what the heck's on this hard drive we want to look at. So we're going to boot our analysis system. We're going to go to that directory that has all our data. Just to keep everybody honest, we're going to make sure all the files are read-only. So basically, chmod a-w is, I always prefer to use the symbolic chmod commands, but if you want to use the numbers, you can figure it out. You want to hash the image and kind of verify that with what you hashed earlier. Either, hopefully, MD5sum gave you a good result. Otherwise, you'll have the hash at least from DCFLDD. Just to kind of make sure everything's good. And now, because hard drives fail and people are fallible, you want to make a backup. Depending on how big the image is, you may want to back it up to another hard drive, which is certainly much more simple. If you want to back up to CDs, this is how you can go about it. You can basically split the image. Well, basically you gzip it, and the output from gzip you pipe to split. So then you're going to end up with a compressed image that's split into, I use 699 megabyte chunks, because everybody uses 700 megabyte CDs these days. And in addition to the actual chunks you're going to want to put on the CD, you also want to put all the text files that you created about what the case is and why you're looking at this hard drive, because you may want to come back later and find this CD and say, well, damn, why do I have this CD laying around? So it's good information to have. You're also going to want to hash all the chunks and have the hash of the original, so you can know later when you reassemble all the chunks that it worked properly. In theory, this is the command to reassemble the chunks. It depends a little bit, because split basically puts letters at the end of the name to designate like which chunk it is. If you have problems where the reconstructed thing doesn't match up with the hash of the original, you may have problems because CAT is putting them in a different order, so you may need to mess around with that a little bit. Incidentally, if you want to use your favorite commercial forensic package or iLook to look at your image, you can split it. And things like NCase can read split DD images. However, they like to have a numerical code at the end of the drive. They don't use the normal split XAA, XBAB kind of thing. They use .001, .002. Jesse Kornblum, among other people, have created versions of split that will allow you to split to numerical file names if you need that numerical extension. Okay, so now we're going to want to mount our image using our NASA Loopback drivers. It's fairly simple. We just basically run a LO setup on the drive. Then we can do an SF disk again to make sure that we're reading the partitions properly. You want to leave the Loopback device mounted for when you run autopsy, because we're going to run autopsy and have it point at those devices. And when you're done, if you don't want to shut down for whatever reason, you should be able to shut down. But you can run this LO setup -D, which will delete the device. I'm going to demonstrate this real quick. I have to do the poor man's switch box here to go to my Linux system. But hopefully it'll come up okay. There we go. Okay, I'm actually in the wrong place. Here we go. Okay, so you see we got this file here, Western Digital, 30 gigabyte .dd. Ah, there it is, right there. That's the file that we're going to want to mount. So we just do an LO setup. Let me make sure I'm typing everything right so I don't mess things up. Oops, loop. A. All you have to specify is the beginning part of the loop device, so loop A, and it will actually create the other devices for you. And then Western Digital 30 gigabyte.dd. And there you go. It doesn't look like it did anything, but it really did. If you run sfdisk now with the old LUS on that device, loop A, you see that we've created additional loop devices. We've got loop A1, loop A2, loop A3, which is basically the same partition numbering scheme you'll see in normal Linux. And you see the exact same partitions that we saw earlier from the output that I made before I imaged it. So we know we've got the right devices, and now we know that the loop device names are. So that's a useful thing to have. If you want to mount the file systems, you can do that. I will just do one real quick. You want to do a -ORO because you want to make sure that the thing is read-only when you do your mounting. And let's mount /dev/loop A2. And we have to give it a name. I think I have. There we go. I have a directory there. So loop A2 image 2. And again, it doesn't look like it did much, but if you do this, you'll see that it has mounted the NTFS file system read-only on loop A2. If I go to my handy browser here, you can see image 2 directory, and there's files that I can look through. So that worked. Now I'm going to go ahead and unmount it because to run autopsy, it does not need to be mounted, so you don't need to have the file systems mounted. I'm going to go ahead and switch back to my presentation here so you can see what I'm looking at. Okay, so now this is what I just did, which is mounting the file systems read-only. When you're done, you can unmount them. What you don't want to do, however, is mount any journaling file systems. And this is for the exact same reason that I talked about before, which is that it updates the journal and messes up your MD5 on your image and all sorts of stuff. Even if you mount it read-only, it touches the journal, unfortunately. So on the next slide, we got a couple options if you really want to mount a journaling file system, depending on how much disk space and time you have. One of the things is you can just basically make a backup copy of your image and go ahead and mount it anyway, because you know you're going to restore from your backup later. It's not going to make any changes to the files. You're still going to see the same data, but it will change the MD5 and just generally makes forensics people uncomfortable to have changes made. So you can do that. The other thing is you can actually extract the disk image using some techniques that I'm going to talk about a little bit later, that not I'm going to talk about, but I'll give you references to later about basically how to extract the partition from the entire disk image. And then mount it. For some reason, if you have a separate disk image and you mount it using standard, basically a mount -ORO, loop, so basically you do kind of doing your LO setup and your mount together, it actually opens the file read-only and doesn't make changes to the journal. I am not sure if this works properly when you're using the NASA drivers. I would say probably use standard Red Hat drivers. And of course, test everything. Don't take my word for it. I would still make a backup. But this is a way that you can look at those images. And part of the reason that we may want to mount the file systems is when you're doing analysis on, for example, a Windows system, you may come across like a Quicken data file or some other stuff that you just have no way of really reading in Linux. So you're going to want to look at it on a Windows system. Well, an easy way to do that, mount all the file systems read-only, share them out using a Samba server, and then access those Samba shares from a Windows system. So you don't have to worry about like making a copy of it and moving stuff around. You just do it all over the network to look at the files that you need to look at. Yes?
I was taught that in your options you should also know anytime, no other time. Because even though you're not read-only, you won't change the file content, right? You just use the capture files and things like this, you're taking them back on.
I haven't heard of that. It certainly wouldn't help. Or, excuse me, it certainly wouldn't hurt. Right. Yeah. Any changes that are made are going to mess up your MD5. So I'd never heard of those options, to be honest. I've probably heard of them a while back, but I've never actually used them. I would say certainly look into it. It doesn't hurt to say all that kind of stuff because that kind of illustrates the point that you never really know what's going on. Even though you're telling it to mount read-only, like I said, the journal is touched. There's other weird stuff going on. That's why you make backups. Yes? Oh, I'm sorry. His comment was there's a couple other options you can use after that -O, which is no M time, no A time. Is that right? Which basically says don't change the modified times on the inodes. Don't change the access times. basically don't mess with anything. I'm not really sure if that helps or not. Yes? No, unfortunately it doesn't. I saw even people, now with regards to actually touching the journal, I know people who have actually, they made it read-only and they made it immutable, which is kind of another read-only kind of thing that you can do with Linux, and it still made changes. So it's some bugs in the code is basically what it comes down to, unfortunately. Okay, any other questions about that right now? But
What about using like a hardware write block?
well, that's certainly something you could do. I mean, that's, especially if you wanted to do more robust things like previews and that kind of thing, I really do recommend the use of a hardware write protection device. Unfortunately, that costs money unless you want to create your own, which I know people have. But it's one of those things that and certainly it's every little bit helps, especially if you're looking at something that is eventually going to go to court. So a network intrusion case is usually more, you just kind of are more interested in what happened, and you may or may not be able to prosecute someone. But if you've got like an internal employee that's got misconduct and maybe doing illegal things on the side, then you're going to be a lot more concerned about evidentiary integrity, and certainly that could be worth the investment. If you are looking at your image, if your image is on something that's write blocked, then yeah, obviously nothing's going to be able to make any changes on it. Unfortunately, I've had problems with write block sometimes, not specifically in Linux, but I have had problems in Windows where you put a drive that's write blocked into a Windows system and it won't be able to access it because it needs to be able to write to it. So there could be problems there. Okay, moving on. I just demoed this, so I'm not going to talk about that anymore. If you want to do virus scanning, that's something that you may want to do. A very good tool for doing virus scanning in Linux is fprot. Unfortunately, it's only free for personal use. Although the developer of Fire claims that he read through the license and was able to figure out that as long as you don't install it on the computer, you can run it. So if you want to boot off the Fire CD and do your virus scanning, you can do it that way. I just put a URL of another freeware virus scanner. I don't know if it's any good or not, but if you want to do virus scanning, that's certainly something that you would want to mount the partitions for before you do that. So quick searching can be done using these tools. Basically, you can use the strings command to dump basically all the ASCII strings out of your image, which may take a long time and take a lot of disk space depending on how big your image is. And then you can look at them to see what basically what's in there. There's a couple of options I'm using on strings here. To find ASCII strings, this -td basically tells you it'll record along with the string at the decimal offset within the file where it was found. So you can later kind of try to track back where it came from. Unfortunately, it's not reading any of the file system structure, so it's not going to be able to tell you later that, well, it came from this file, but at least they'll give you an offset within the thing, and if you really want to, you can track it down. One of the neat things you can do is actually look for Unicode strings. For those of you who've used a lot of Windows stuff and done forensics, you'll know that a lot of Windows internal data structures now are stored in Unicode, which means that normal strings aren't going to find it. That's the version of strings that comes with Linux actually supports this -el, that's a -e space and then a lowercase l, which says it wants to look for little endian, basically Unicode strings, which is the Unicode strings that are used on Wintel architecture. If you were looking at, for example, a Spark system, there's a different option you need to use for big endian systems. And that will just dump, again, all the stuff to a strings file, and then you can later use grep to search through those strings files that you've created. You can use grep to search directly on the image, but that's going to take longer, and it's going to take longer every time. At least this way you create the strings file, and then you can search the strings file later fairly quickly. You can do ASCII searches within Autopsy, but you cannot do Unicode yet. Brian wants to add that to it, but he hasn't yet. You can run Foremost. Obviously, we installed Foremost. We're going to want to run it. The way that I use it is you want to copy the foremost.conf file into the directory that you're in, because you're going to want to alter the configuration, and you're also going to have a record of what type of configuration was used on Foremost. So basically, you just copy that file in there, edit the file. It's fairly easy that you can basically say what kind of files you want to search for. By default, I think it searches for graphic files and the other fairly common ones. There's some other esoteric stuff that's in there that is commented out that you have to uncomment. You run foremost -o. You give it the, this here is an output directory. And if that output directory is, if it's not there, it will create it for you. If it is there, it must be empty. And that is a feature to ensure basically evidentiary integrity. The -V option here, it says basically give you verbose output, tell you what it's actually doing. And the serial number here, that's just the data file that you're reading into there. So Foremost will just basically spit out a whole bunch of graphic files. If you want to mess around with Foremost, that ext3 file system image that's on the Black Hat CDs has some image files in there that have been deleted. You can run Foremost on there and extract most of them. You can also run it on the Loopback devices if you want to just look through one particular partition. There's nothing wrong with that. You can also run it on the free space that is extracted by Autopsy. Autopsy has the ability to create what's called a DLS is the extension. It's basically the free space from a partition. And some people recently integrated Foremost, actually within like the last couple weeks, into Autopsy. Brian Carrier has been reluctant to do that in the official version of Autopsy because Foremost currently doesn't run on Solaris or OS X, whereas everything else in Autopsy does. He's kind of just trying to keep everything together. And that's actually something I meant to mention at the beginning of the presentation, which is that a lot of the techniques and tools that I'm talking about here don't just run on Linux. They will run on other Unix-type operating systems. So if you want to use Solaris or use OS X or whatever, most of these tools will work. Not all of them. Particularly the NASA Loopback drivers are very tied to Linux. And so you're going to have to kind of decide what you want to do there. A couple of issues with Foremost, and I'm glad Jesse's here because I've been meaning to talk to him about these. One of them is that it creates this directory, this output directory immediately if it isn't there, and then it creates an audit file in there. The problem is if you specify invalid options or you mess something up, it creates this audit file and then it basically craps out, doesn't do anything. But then if you go back and fix your typo, then it won't run because the audit file has been created in that directory, the directory is not empty. So just be aware of that. That's the only real problem with Foremost. Other than that, it's a great tool. One of the issues with Foremost, just to be aware of, is that it doesn't look at the file system. So it's not just going to extract deleted files. It's extracting every file on there. So if you've got logical files and deleted files on there, it's going to get both. And that's one of the reasons you may want to look at the DLS file, the free space that Autopsy extracted. And the other obvious issue is that the file must be contiguous in order for Foremost to find it. If you're looking through there and it finds a JPEG header, and then it's going through there, and then all of a sudden there's like a text file in the middle, and then there's JPEG footer later, it's going to get the whole thing, including that text file in the middle. And it's kind of a mess. So if you may have problems. It's not a perfect system. It's not going to extract even all the logical files properly because it's just making some assumptions on what's the data format's in. And that's just all disk carving tools are that way. So those aren't unique Foremost issues. Okay, now we're to kind of towards the end of the presentation when we're talking about SleuthKit and Autopsy, which are the main tools you're going to want to use that have most of the features. I'm not going to be able to cover the entire details. They're fairly complicated. I'm not really going to talk at all about SleuthKit because Autopsy kind of uses SleuthKit behind the scenes, but you can use a lot of the SleuthKit tools independently. I'm not going to worry about that. I'm more concerned about the GUI environment because it's a lot easier to use. Basically, you start Autopsy, you just go into the directory that it's in, you run it, and this -D, and then the evidence locker that we created, because again, you want to make sure all your evidence is being written into that directory on your image drive. You're going to want to start a web browser. It says here as a non-root user. It would be safer that way. It doesn't really matter so much depending on how well you're connected. Autopsy will display a URL you connect to with that. And also just be aware that potentially dangerous files, which is basically HTML, are sanitized by default within Autopsy. So if you look at a web page that, say you look at yahoo.com, it's from someone's internet cache, it isn't going to go out to Yahoo and extract and fetch all the graphics that are in there. It actually modifies the thing. You can actually go and look at the original file without the sanitization if you want, but it's really designed so that you're not making network connections. And again, your forensic system really shouldn't be on the network anyway. Okay, so that's what Autopsy looks like, the initial screen, and I'm going to show you that on my other system here. So give me 1 second to switch computers again. Now remember, we've already got our NASA Loopback device basically thing set up, and screen's blank, that's all. Okay, so I got another shell here where I'm in the Autopsy directory. Being that I just have one hard drive on this system, I don't have a separate evidence locker directory, so it's just using the standard /evidence lock. And it gives you this URL. There's some other options you can use when you start Autopsy, and it's a pain to cut and paste here, to specify what hosts are allowed to connect and all that kind of stuff. Autopsy really is able to do remote analysis, but again, I'm kind of just keeping to the simplest situation where you want to look at the system you're on. And it comes up and it gives you this nice little screen. So now a little bit about autopsy, the terminology that autopsy uses, which is actually in your slides, but I'm just going to talk about it because I want to switch back. It has a case. What it's considered is kind of what I'm considering a case, which is like if you've got an intrusion that all happened in one day to 3 systems, that might be one case, and you would have like a case number or identifier with it. It has what it calls a host, which is basically one computer, but it may have more than one drive and more than one partition, and then it has what it calls an image, which is basically a partition. So you've got case, host, and image. So we're going to create a new case. I'm going to just go ahead and give it a name, Black Hat Demo. You also have to put in some investigator logins. These, you can't have any spaces in them, so I'll just put Chuck W. And hit new case. You can put a description in there. It gives you a little thing saying, and basically what it's doing is it creates directories underneath the evidence locker to store the administrative data about this case. So this Black Hat Demo is actually a directory name underneath the evidence locker. So for that reason, a lot of the things that you do in autopsy, you need to be careful about putting things like spaces in there because it's creating directory names, basically. And it also creates configuration file and that sort of thing. Okay, and I've got some old ones on here, but I'm just going to look at this Black Hat Demo that I just created. And now I'm looking at the case now, but there's no hosts that have been added. So I have to add a host. You put a host name. I usually just use like an IP address. That's as good of an identifier as anything else. One of the things you need to put in here is a time zone, which is a little, it's basically a standard Unix type time zone identifier. I'm not real sure exactly all the syntax, but I know the gist of it is for Eastern time, you do EDT 5 EST. And you can also put a skew for each host as far as how far the time on that host is off from a universally accepted time. So if you've got 3 systems that were compromised and one of them's 5 minutes fast, the other's 3 minutes slow, then you can kind of compensate for that and try to put everything together in one timeline. But I'm not going to worry about that. It also has, in addition to the NSRL databases, you can have your own hash database of alert files, which is basically bad files that you're looking for. And you can also have a hash database of known good files. So if you come across, for instance, it's a Linux Red Hat 8 system that was compromised, you can create your own hash database of known good Red Hat Linux version 8 files and create your hash database there to basically very much cut down on the number of files you're going to have to look at. So now we add a host. Again, it gives you a little screen here telling you what you just did. And now we're coming to here what it calls the host gallery. So now we can select which host we want to look at. We just have one, so we're just going to look at that. You can put in which investigator you are, so you can have multiple investigators, and it creates an audit file to say who did what at what time and all that. Okay, now we created our host, but there's no images right now in the host, so we want to add our images. So just click on Add Image. Image location. Now this is where we're actually going to specify the loopback device that we want to look at. Because one of the things about autopsy, and this is also on your slides if you're following along in there, is that it requires that you have images of individual partitions. And that was kind of the whole point of why we installed these NASA loopback drivers, because we want to be able to look at the image of an entire disk. So by pointing it at the NASA loopback drivers, you'll be able to look at those individual partitions that are basically dynamically extracted by the drivers without having to create separate files. In the notes there, you'll see a slide that talks about this, and it has a couple websites you can go to for information about how exactly to go about extracting the partitions from the file, from the universal image if you want to. So what we're going to do is we're going to point it to the loopback driver. So I'm just going to say /dev/loop_a1. And we want to say that we want to symlink it into the evidence locker. So we don't want to create a copy of the image. We want to just symlink it into there. Now if we go back to our SF disk output, which is right over here, we see loop A1 is a Linux system. I actually know separately that it's an ext2. The mount point, I usually just leave it / for most of these. One of the things you'll have problems with, on some Windows systems, I tried doing things like C: and D:, and the colons really kind of confused autopsy, so I usually just leave everything /. You can calculate the MD5 of each image as you're adding it. I'm going to hit ignore because I don't want to waste time waiting for MD5 to calculate. And now we've added our image. I'm going to go ahead and add image for the other two files real quick, so that the other two file systems. So I'm just going to loop A2, which is a symlink, and that is an NTFS system. And again, I'm just going to put mount point as slash, ignore the MD5, add. Okay. And you probably could just hit add image there. But I'll go back. Okay, so slash dev slash loop A3. And A3 is a FAT32 file system. Okay, so now we've got our 3 images added. Now we'll go ahead and go back to the host manager here. So you can select any one of these 3. Unfortunately, you can really only look at one image at a time. So you can't, for example, search all 3 of the images at once or look at files from all 3 images at once. It's just a one at a time kind of thing, which is a bit of a pain if you're used to being able to look at more. First one I want to look at here is loop A2. And you just kind of select that file there and hit OK, and that's going to bring you into a rather empty looking screen that you want to look at here. So, and it's just basically telling you select what you want to do. So I want to do file analysis, which is basically the basic file browsing where you can look at what files are on the system, that sort of thing. And you can see here, this is a, let's see, loop A2 is an NTFS file system. So you're seeing a lot of these NTFS kind of things, $sign files and information and stuff, but then you also see some actual directory names down here. If you click down here on expand directories, you'll actually get a nice little directory tree. I'm going to drink water while that's coming up. So this gives you all the directories that are on the file. Basically all the files that are on these partitions are stuff I copied off of a Red Hat install CD, so it's kind of DOS utilities and stuff. You just kind of float around, click on a directory there, comes up. Here's one file that I created that I know has got some information of interest, so I'll go ahead and click on it. Basically what I've done is create a little drug information in various text files on this thing, so we can do some searches and it'll actually come up with something fairly interesting. So we know that this file 1.txt contains this sentence here: I left the drug money in the mailbox. One of the other interesting things you can do, if you click here that says all deleted files, you can look at deleted files. It's really sketchy depending on the operating system how well it's really able to recover deleted files. It seems to have some significant problems on NTFS, but there's other ones that it'll come up with okay, but some of them do come up that you can see things. These are actually ones that are in the recycle bin, and it gives you some information. But the other thing you can do here is you can, in this view directory box is where you can put in a directory. So I want to look at the DOS utils directory. Hit OK, and it should take me to that directory. So it's a nice little quick way to get around if you need to. One of the features of Autopsy is you can create notes. So you can create a note about this directory, say interesting. Unfortunately, I've had a lot of problems with the ability to create notes. Let me see, I'm going to click OK here and see what happens. I was having problems with it last night as well. So the notes seem to be a little broken, which is unfortunate, which basically, when it works, it's great because you can basically say, well, this is an interesting file, this is an interesting file, and then be able to later go back and look at all your notes and see what files are of interest. But for some reason, I click OK and nothing happens here. Let me unclick this and see what happens. No, still nothing. So unfortunately, that's not really working right now. I need to email Brian about that. Keyword searching is obviously something that you're going to be interested in. We just saw that sentence that contained the word drug, so I'm going to go ahead and look for the word drug again, because it's actually a rather interesting result. I'll talk a little bit more about the keyword searching options there in a second, next time I go back to it. It doesn't take too long. This is only about a 100 megabyte image that we're looking at. So it's chunking away for a little while, and eventually it'll come up with a list of where it found the word. And it only found it in 2 places, but the 2 places it found are rather interesting, actually. So you click on one of them there, and it says ASCII. Where I clicked on where it said ASCII there. And you can see that all the way over here, you see the sentence that we saw there. I left the drug money, yada, yada, yada. And it says up here, this is the cluster number that it's contained in, and this is the fact that that cluster is allocated to a file. If you click on Find Metadata Address, it will tell you where that file is, what file owns it. And it's kind kind of funny here because it actually belongs to this file called $log file, which is basically the equivalent of a journal for the NTFS file system. So because that file was created and then deleted and then the system was shut down shortly thereafter, the file information is still in the journal. If you click this other one here, you'll see another instance of the same text, which you see over here. It says I left the drug money here. It's also allocated to another cluster. If you click Find Metadata Address, this is going to come up and tell us that it's in $MFT, which is the master file table for NTFS. The reason that the data is in there is that I've got, because it's a very small file, it is actually an embedded file within the MFT. So there's not separate data blocks that are allocated to that file. It is really just embedded data within the master file table, which is a very efficient way of storing small files that NTFS uses. Unfortunately, there's no easy way to come back from this to the actual file name that we saw this text in before. And there may be a more complicated way to do it, but I haven't quite figured it out. But it is useful information nonetheless. I'm going to close out of here and look at another, the other loopback thing here, number A3. This is a FAT file system, and I'm going to do a little bit of searching here to show you how you can search for multiple words at the same time. I mentioned the keyword options that I forgot to talk about earlier. This here is just where you put the string that you want to search for. You can click here to say whether it's case insensitive or case not. Normally you would want to put insensitive, but I just leave it because I want the searches to go fast. But one of the options you do want to use for what I'm going to do now is regular expressions allow you to search for multiple words at the same time. So I am going to search for 3 words right now. They are drug, cocaine, and pot. And if you do this without clicking the regular expression, you're not going to find anything because it's looking for literally those bars there. But by the vertical bars allow you to search for multiple words. And it chunks along for a little while. It's going to take about 3 times as long as it did last time. This is another 100 megabyte partition. But it does come up with some different types of files that kind of let you show kind of how Autopsy views things. Sure. Mm-hmm. Mm-hmm. Right. Well, it's going to depend on the email file that you're using, to be honest, the email program, because if I'm not a real expert on those kind of things, but my guess is that if the email program you're using kind of keeps everything as a separate email, then the deleted email will be a deleted file and Autopsy may be able to find it. If the email program has some sort of database that it uses and it puts everything in, it may just mark them as deleted and still be able to, and the data is still in there. So the keyword searching would still find it really either way, to be honest, as long as it hasn't been overwritten. But it may find it as part of a larger allocated database file, or it may see it as a separate file that's been separately deleted. Does that answer your question? Excuse me? There's a couple searches that you can do specifically for things like IP addresses, but email addresses you would probably just have to craft a grep expression and look for email addresses and search through them, which is not all that complicated to do, just a bunch of letters and numbers and then an @ and letters and numbers and that sort of thing. Sure. Mm-hmm. It's not directly supported, but there are other tools I'm going to talk about at the end of the presentation that can look at PSD files. But basically what Autopsy does is it allows you to look at all the files, and that's kind of what I talked about earlier, that you may well have a lot of data files that you're going to have to look at with other tools, because Autopsy doesn't have the ability to interpret all these other data files. It can do the basic stuff, text files, HTML, graphic files, that sort of thing. But you may well have to use other tools. But the good thing is that this keyword searching should allow you to kind of target what you want to look at, hopefully. Anyway, so I've got 3 or 4 hits here that I want to show you real quick. This is just found the word drugs. If you click on Find Metadata Address, it says this is actually a regular file. It gives you the file name that actually contains on it. And this is a FAT32 system, so it stores things a little differently. It's not an embedded MFT file. This next one here is actually a deleted file. It comes up and says not allocated. and then if you click on Find Metadata Address, it will tell you the name of the deleted file. So you can actually go within the file analysis and find that file and be able to see the same thing. The next one here is a little strange, and I'm not even sure exactly why this works. I need to ask Brian about it. It's found the word drugs in this file. It comes up with kind of the strange format. It says orphan file /trans. The trans was actually the original file name that this file was saved as. It was in a directory that was deleted. The entire directory was deleted along with all the files that are in it. So somehow Autopsy was able to find the directory entry and know that trans was the name of the file, and this is the data that was in that file. And I'm not quite sure how it does that. I mean, there are ways to do it. I'm just not exactly sure how Autopsy does. And the last thing I'm going to show is this is actually a recycle bin entry. This is a file that's in the recycle bin. The file name has been changed because that's kind of the way DOS sends stuff to the, excuse me, not DOS, Windows. This I think was Windows XP that did this. Sends stuff to the recycle bin. It renames the file, but it has a little what's called an info2 file that stores all the data about how what file the original file name was, so that you can restore them later if you need to. And that's about all I'm going to show about Autopsy. I'm going to talk a little bit more about some other stuff. There's some sorting you can do here with file types to go through and do some sorting, kind of analyze, what graphic files are there. Some interesting stuff you can do with that. The image details here doesn't have anything to do with graphic files. It talks about the details of the image that you're looking at. You can see this is a FAT file system. There's the volume label. It's FAT32. It tells you all the information about the different sectors in the FAT, the actual FAT. Metadata tells you about basically how you can find directory entries, inodes, and that sort of thing directly. The data unit does fairly similar stuff, but you can find actual sectors on the drive using various ways. And that's kind of what that is. There's also some interface here. If you go at this point, you can look at the file activity timelines to kind of generate timelines of when files were accessed. You can look at the image integrity, lets you basically verify your MD5s. Hash databases is kind of uses the hash database I talked about earlier. Event sequencer does more event timeline type stuff. And then this is where you should be able to go and view the notes that you created, but it doesn't work. Okay, question, yes? When you run Autopsy, it shows it on the screen here. So I ran Autopsy in a command shell, and it gives me the big URL that I'm supposed to go to. Okay, I think that's pretty much all the slides I have on Autopsy. I've got a few other slides on other stuff, and I've got about 8 minutes left. So I'm going to run through them quickly. They're in your book, so you can look at them if you want. One of the things to note is that deleted files are showed in two different ways in Autopsy. There's the bright red files that are basically ones that I believe, let me make sure I'm telling you the right thing. The bright red ones are ones that the data blocks have not been reallocated. So there's a fairly decent chance that may actually be the data that was originally in the file. A dark red entry indicates that the data has been overwritten and is allocated to something else, and almost certainly is no good. So just be aware of that. More things, keywords, and I talked about that. Okay, in conclusion, here's some other potentially useful tools, including one that will look at PSTs, someone was asking about. A lot of these, as I mentioned, are written by other people, including Jesse wrote MD5 Deep, which is basically a nice way to handle recursive MD5s. MD5 sum doesn't handle recursion very well. And then, like I said, you can read all those. Several of these are part of the openforensics.org project, which is run by some people from Foundstone and some other people that basically are looking at examining Windows-type data files in a Linux environment. But my usual opinion is that you should really, if you're looking at Windows files, you should be looking at it in a Windows environment just to see what's there. There's some other tools that are coming out, including stuff from the Open Forensics guys. They're coming out with something called OpenDD, which has now been renamed to NED, Network Evidence Duplicator. It's a menu-driven version of DD, which allows you to not have to worry about little typo destroying your evidence. And it adds some other stuff, doing remote analysis, remote imaging. It's not there, it's not done yet. I'm not sure how it's all going to work, but it does have an analysis system that goes along with it, Rex, which is also supposed to be cross-platform. I mentioned Penguin Sleuth already. There's a strange thing that was created by the Australian government, this forensics and log analysis GUI. I looked at it very briefly. It only came out about a month ago. It could be interesting. We'll see what happens. I'll leave that up to you to look at it. Knoppix STD is another secure tools distribution version of Knoppix that's out there. But here's some good resources here. The HoneyNet project, which actually spoke in here right before me, has some scans of the month that deal with forensics, particularly 15, 24, and 26. If you go to their website there, you can find them. So it's a great way where they've basically got some floppy disk images that you can look at using these forensics tools and be able to see if you can find the things that you're supposed to find. Brian Carrier actually did some great case studies using autopsy on those scans, and if you go here, you'll find it. Brian Carrier has a great newsletter as well, the SleuthKit Informer, that has information about how to use SleuthKit, and it includes, in number 2, the information about how to extract partitions from a whole disk image. There's also the Linux Forensics Users Group, which is a Yahoo group. The website's there, which has a mailing list as well, which is a very good source of information. I mentioned NSRL. A few websites here which all get kind of confusing. There's openforensics.org, there's opensourceforensics.org, Penguin Sleuth has its own linux-forensics.com. The Corners Toolkit, which is really out of date if you ask me, with the SleuthKit and autopsy being out, but if you want to go back to the original TCT, there's the website. And that's pretty much it. Any final questions? I know everyone's wanting to go to lunch. Yes? RAID arrays? It really depends, to be honest. Probably, if it's a hardware RAID, you can pretty much use the tools that I've talked about today. If it's a software RAID, you're probably going to have to set up a special system that has the ability to interpret that RAID and then make the image. Any other questions? Okay, well, thank you very much for coming. Everybody, go get some lunch.